In Part 3 of Lecture 7, we will discuss the banker's algorithm. The problem with using resource allocation graphs is that they are hard to turn into programs if there is more than one instance of a resource. In that event, we will use something called the banker's algorithm. A banker does not want to have too much cash on hand because it isn't earning interest or any other return on investment. But he or she must have at least enough to meet the demands of the day. In figuring out how much cash he or she needs, a banker can take into account the amount of money coming in as well as how much is likely to go out. The estimates should be as conservative as necessary because it is better to keep too much cash on hand than to run out. The algorithm that you see here tells us if a given state is safe. It requires that we must have at least one process that can get everything that it is allowed to reserve. Then we pretend to free its resources and see if there is a process which can get the rest of what it may need. We continue this until every process is able to complete its execution or until we're certain that they can't. In the first case, the system is safe, and in the second case, it is unsafe. The previous algorithm tells us if the system is safe, but will it be safe if we allocate a resource or more than one resource to a process? Let's pretend to allocate the resource or resources and see if the system is in a safe state. If it is, we'll do the allocation. If not, we won't. Let's look at a simple example. Imagine there are three processes which have been allocated our one resource as shown on the slide. They each have a maximum allowed allocation as shown. The first step is to calculate what they might need. For process P1, it is 4 because a maximum of 4 minus an allocation of 0 yields 4. For process P2, it is 5 minus 2, yielding a need of 3. For process P3, it is 8 minus 4, yielding a need of 4. With the sequence P2, P1, P3, we have determined that the system is in a safe state. With 4 instances of the resource available, we could complete any of the 3 processes. Let's say that we complete P2 first. Now we can free 2 that P2 is holding. With the 6 available, we can complete either P1 or P3. Let's complete P1 first. Since there is nothing to free, we don't change the amount available and we complete P3. Let's allocate 2 instances of our resource to P1 and 1 more to P2. With only 1 instance of the resource left, there is no process whose potential need can be met. So we cannot be certain that any will run to completion. The system is in an unsafe state, and the allocation was not a prudent move. Let's take a look at a more typical situation. There are 3 different types of resources, A, B, and C. Shown here is their current allocations, the maximum allocations that they may request, and what remains available. Our first step is to calculate the needs. P0 has 0 instances of A, 1 instance of B, and 0 instances of C. It has the right to 7 instances of A, 4 instances of B, and 3 instances of C. 7 instances of A minus 0 allocated instances of A equals a need of 7 instances of A. 5 instances of B minus 1 allocated instance of B equals a need of 4 instances of B. 3 instances of C minus 0 allocated instances of C equals a need of 3 instances of C. We now do the same for processes P1, P2, P3, and P4. When we finish, we see that P1 can get everything that it may need, so it will run through completion. After we reallocate the 2 instances of A that P1 is actually holding, we have 5 A's, 3 B's, and 2 C's. With this, we can satisfy P3, and it can run through completion. Once P3 finishes, we reallocate its 2 A's, 1 B, and 1 C, making 7 A's, 4 B's, and 3 C's available for reallocation. Now we can finish P4. We can now free up the 2 C's that belong to P4. And now we have 7 A's, 4 B's, and 5 C's. This is enough to allow us to complete P2. Lastly, we free up the 3 A's and 2 C's that P2 has. This will leave us with enough to complete P0. There is a sequence in which we can complete all the processes if they do need the maximum allocation. The system is safe. Let's examine a request of process P1 for 1A, 0 B's, and 2 C's. Since this is less than what is available, we have the resources available for the request, but will it leave us in a safe state? Let's pretend to allocate it. This leaves us with 2 A's, 3 B's, and 0 C's available. We have enough for P1 to run to completion, even if it needed its maximum allocation. After deallocating its 3 A's and 2 C's, we would have 5 A's, 3 B's, and 2 C's available. With this, we could run P3 through completion. Then we could free its resources, which would give us 7 A's, 4 B's, and 3 C's. With this, we could easily complete P4, P0, and P2. Thus, this request can be made without placing the system in an unsafe state. If P4 were to request 3 A's and 3 B's, we would be unable to fulfill the request because we do not have the resources available. We are 1 A short of what is needed. Let's see what happens if P0 requests 2 B's. It's less than the available resources, but does it place us in an unsafe state? Let's add the 2 B's to P0's allocation and recalculate its need and what would be available. The problem is that 2 A's and 0 B's and 0 C's leave us unable to meet any possible requests by other processes. This request won't be granted because it would place us in an unsafe state.